So after looking at the probability, so after trying, so yesterday we were able to calculate the mean and probability of a sample distribution in terms of proportion. Now let's use that information to calculate our actual probability. So first example, suppose that 13% of the population is left-handed. A 200-seat school auditorium has been built with 15 lefty seats that have been built and desks on the left rather than the right side of the chair. In a class of 90 students, what is the probability that there will be not enough seats for the left-handed students? Before we can find the probability in terms of our normal model, we must make sure it meets these conditions. So first, is it independent? So yes, I can assume that if I were to grab a right-handed seat, that doesn't affect whether or not I grab a left or right next time around. So we'll assume that that's independent. Randomization, is it random? Yes, I can assume that I'm picking these chairs by random. 10% condition. Notice I'm looking at 90 students here. So in order to meet this 10%, I need to make an assumption that my school is no more than 90. You know, I'm just going to start over. So, after we got done figuring out how to find the mean and the standard deviation of a sample distribution in terms of proportion, let's take the information to find our probability. First example, suppose that about 13% of the population is left-handed. A 200-seat school auditorium has been built with 15 lefty seats. Seats that have been built in the desk on the left rather than the right arm on the chair. In a class of 90 students, what's the probability that there will be not enough seats for the left-handed students? So in order to calculate this using our normal model, we must meet these conditions. First condition, independence. Is my grabbing my seat independent? So for example, if I were to grab a right-handed seat, does that affect me grabbing a left or right-handed seat next? No, it shouldn't. So we'll assume that this is independent. Randomization. We must make sure that we select these seats by random and not just going out and picking and choosing on purpose. So we'll say yes for that condition. 10% condition. We must make sure it is less than 10%. So I have 90 students, which means I need to make sure that my school is at least 900 students. So let's go ahead and assume that our school is about 901 students or more. We can use this school, which is about 2,000 students, so it will meet this 10% condition. And number 4, do I have at least 10 successes and 10 failures? Well, to calculate that, we need to take our n value, so n in this case is 90. Probability for success is our left-handed people, and that is about 13%, so 0.13. And probability of failure, which gives me a probability of 87. So n times p is success. So 90 times 0.13. That equals 11.7. So yes, I have more than 10. Now my failure. 90 times 0.87 and times 0.87 is 78.3. So yes, that is greater than 10 as well. So I meet my success failure condition, which means I meet all of my conditions. So I can go ahead and assume this follows a normal model. Now, a couple things. You can do this by hand, which here's the formula by hand. I need to find my z-score, which is p hat, where the p hat is x over n. So that is, how many seats do I have total in my auditorium? 15. Over, sorry, how many left-handed seats I have total over how many I have total in general? 15 over 200. That is going to be my p hat. Oops, 15 over 200 gives me 0.075. Oh, sorry, not 200. Two ways to solve this. We can either do it by hand or by a calculator. If you're going to do it by hand, we must first find the z-score and compare the z-score to our normal model. To find the z-score, I need my p hat. P hat is my x over n. So my x value is how many lefty seats I have total, which is 15, over how many students? I have 90 students. So 15 over 90 gives me 0.167. That is my p hat. I'm subtracting that from p. So I found p to be 0.13. And dividing it by this is our standard deviation. So the square root of p, 0.13 times q, 0.87 over n, 90. Now calculating that gives me 1.06. I need to take this number, look in my z-table chart, and that's going to give me a probability of 0.8554. Now, what does that tell me? If I were to draw my normal model, I want my p to be the line of interest. So that's going to be your p hat, which we found that to be, we'll come back to that, 0.167. So this is my p hat at 0.167. And I'm looking for not enough seats. Not enough seats means greater than or equal to. So I'm looking for all of this information on my normal model. So I'm going from 0.167, that's my lower bound, all the way to this number here, infinity. So with our z-table, it calculates this portion, which is why we're subtracting 1. So we're subtracting the total from this portion will give us this space right here, which I see is roughly 0.1446, so 14%. That's if you want to do it by hand. If you do it by a calculator, let me bring it up. You are going to use this table right here. So A is between values, that's not what we're trying to find. B is greater than or equal to. As you notice, that's what we want to find. Not enough seats. Seats that are greater than or equal to our p hat value. So to put this in a calculator for B, looking for a greater than value, we'll go to norm CDF, so second distribution, norm CDF. My lower, which is going to be my 0.167. My upper is going to be the positive affinity, but to put positive affinity in the calculator, we need 1 to the e power 99. That's the highest number you can ever put. And then my mean is 0.13, percentage of lefties. And my standard deviation is going to be 0.035. And paste. And as you see, I get 14.5%. Roughly the same. It's not going to be exact because, again, we're not calculating to infinity. We're only calculating to that power of 99. There's lots of numbers after that, so it's going to be a little bit off as we're in the thousandths or 10,000ths of a decimal. Next example. Just before a referendum on a school budget, a local newspaper polls 450 voters to predict whether the budget will pass. Suppose the budget has the support of 51 of the voters. What is the probability that the newspaper sample will lead to predict defeat? So, is it independent? I can go ahead and assume that each vote's independent. Just because I vote yes doesn't mean you're going to vote no, or vice versa. Assuming we don't know each other. Randomized condition. I'm going to go ahead and assume that the votes are going to be randomized. So I'm not just going to grab all the yes votes. I'm not going to grab all the no's. I'm just going to make it random. 10% condition. I have 450 voters, so I should assume that I have roughly more than 450,000 total. I need less than 10% condition, so I want to be more than this. Let's assume that. Success and failure condition, so my n in this problem is 450. Probability for success is 0.51, vote no yes. Probability for failure is vote no, 0.49. So I get, for success, NP, so 450 times P, 151, that is 229.5, which is a lot larger than 10, so that works there. And 450 times my failure, I need more than 10. That is going to be 220.5. So again, that's greater than 10, so it passes that. So all my conditions are met here. Now I need to find the probability. That will lead to a defeat. So I have my normal model, have some average here, my P naught, which the P naught is yes or no, pass or no. So the P naught is going to be roughly a 50-50, so 0.50. That's what we can expect, 50% of the vote. So either will lead to a win or a defeat. So I'm looking at less than or equal to this value. So I want all of this shaded region. And let's see, what is my P? So my mean is the 0.51. My standard deviation is going to be square roots of success times failure, so 0.51 times 0.49, all over n, which is 450. Which equals, let's see if I have it here, 0.024. Now again, if you do this by hand, here's your z. Take your p hat value minus your p, divide by the standard deviation. I get negative 0.042. I would want to go to my z chart and see what is that probability. Since the z chart is based on less than value, so this, which is what I'm looking for, I can accept this probability. I don't have to subtract 1, which finds the greater than. So roughly 0.337. So about 33.7% chance that I'll predict a defeat. If we're going to do this on the calculator, like so, I want to go second distribution, talk about a normal model here. Now my lower is going to be here, negative affinity. And to put that in the calculator, that's 1E99. And my upper is here, 0.5. About a 50-50 chance I'll get a yes or a no. So that is negative 1E99 for negative affinity. Upper is the 0.5. My mean is 0.51 with a standard deviation of 0.024, and I get, same thing, roughly 38.8%. That was 38.7. Again, we're not working with numbers to infinity. We stop at negative 1 to the power of